Hi, everybody. So this is chapter 14 of Bio 101, and this chapter answers the question, is the human population too large? So we're going to be looking at some population ecology, excuse me, some population ecology questions. And so you have a set of learning outcomes to be able to explain population growth, factors that influence human population growth. I explain why populations go through something called a demographic transition. So you have to know what that is to explain it, and then define carrying capacity and list the density dependent and independent factors that affect growth. And then, this could actually be two objectives: discuss factors that affect Earth's carrying capacity for humans, and then discuss the potential future of the human population and what factors would help reduce growth rates. Growth rate, we are one population. So in ecology, this is the study of interactions among organisms and between organisms and their environment. So it's the whole thing. And you can have like local ecology, like your backyard or a park, or a fishbowl. Or you can have like a larger area ecology, like a state or a region, or a region. I guess you could have a country, but ecology isn't usually defined by man-made borders, right? It's defined by biological borders. And then you just have the global ecology. Now, populations are all the individuals of a species in that given area. And in this case, we're talking global. So we're talking all the humans on the planet. And speaking of, do you know what the approximate population of humans on the planet is? 7.2 billion, according to this book from 2016, I think it was. And this estimate is from 2012. I remember when I was studying soil bacteria and their relationship to agriculture, the carbon cycle was particularly important, and farmable land and how rich it was in carbon was important. And I remember reading a prediction to 9 billion people. So this doesn't surprise me too much. But the question is, can our planet support that many people? And would everybody have the same level of support? So another thing we have to look at is the growth rate. Okay, so the growth rate is little r for rate, and it's a function of the birth rate and the death rate. It's the birth rate minus the death rate, right? So if more people are being born than are dying, your growth rate is increasing, or your growth rate is positive. And then if there's more people dying than being born, then your growth rate is negative. The growth rate of humans over a long period of time is, has varied, but it's been about 0.1%. And so we've had this different populations, in the 1750s, the growth rate was really high. And so then population's size started increasing. And now the current growth rate is 1.2. So it used to be 0.1 and now it's 1.2. That's an order of magnitude and then some bigger. Our current population, 86 million people added each year, and 3 people added every second. That means that we are growing in an exponential rate. So exponential is when you have this J-shaped curve, when you plot time over something and it makes that shape. That's exponential growth. And we are growing exponentially. Now, there's another term that when we talk about population growth, we use this term called demographic transition. And this is when birth rates drop towards death rates. So it's not numbers of births and numbers of deaths, it's rates of birth and rates of death kind of the same thing in this sense, but I just want to point that out. This visual is much more helpful than thinking about words. So if you have the relative birth and death rates, transition is when the birth rates drop towards the death rates. So what limits a population growth? Well, we know that there are limits. We know that no population can grow to unlimited numbers. And those limits are due to something called the carrying capacity of that environment. So in this case, the whole Earth. The carrying capacity is the maximum population that can be supported indefinitely in that environment. So the maximum population that Earth can hold of people, and that, populations can grow exponentially, and that's going to be limited by food, water, shelter, and physical space. There are density dependent factors that limit carrying capacity, or that limit population, sorry, not carrying capacity, limit population. And those things are going to be limited food, increased risk of disease, and increased waste. So for example, like the Daphne I hear, they're going to have they're photosynthetic. Daphne photosynthetic? No, they're not. They're heterotrophs. So they might run out of food, but even if they don't, if they're in a closed system like the fruit flies, their waste might increase until it eventually poisons them and they die. White-tailed deer, their populations get so large that they're at risk for a prion disease called chronic wasting disease, at least here in Michigan. Which factor would be density independent then? Doesn't matter how many they are, this factor would still affect the population. It would be drought, yeah, drought. Other density independent factors include temperature extremes and natural disaster. And what happens is when these things happen, then competition for resources increases, and that's going to affect the population. That then becomes limited food supply, right? Or other resources. So when we're trying to predict what Earth's carrying capacity is, how many people can the Earth support? You kind of have to think about what potential populations we might have. We might have a low growth rate, a medium growth rate, or a high growth rate. And determining when a particular population is near carrying capacity, we can use a few things. If it's a declining growth rate, then that's going to be due to, decreased death rates and decreased birth rates. If it's a decreased death rate despite rapid population increases, then people aren't running out of food. Whereas if you have declining birth rates, that's just choosing to have fewer people. So one of the ways we can estimate the Earth's carrying capacity is to use something called net primary productivity, which is basically the amount of food and energy available. And that's used, or it's calculated using plant growth over a single year. And humans use 1/4 to 1/3 of the entire plant growth per year. And so the carrying capacity of Earth might be as high as 20 billion, but that would be only if humans were supported by photosynthetic products, right? So if we only ever ate plants. And then on that, it's also, if we use the net primary productivity to estimate carrying capacity, we're not thinking about other things. We're not thinking about clean water, clean air, energy for other things that we need, and other limited resources. So that's difficult to estimate and apply. So we can't use net primary productivity as our only way of estimating and just say, well, 20 billion people, we're good to go, because there's a lot more that needs to be considered. And then you also have to think about we're not the only ones on this planet, right? And so, yeah, while all of those plants that would assume that we're eating, the bushes in our front yard and the grass and things like that, stuff that we wouldn't ordinarily eat. And it would also assume that nobody else has to eat anything. And we know there are lots of other animals on this planet, right? And so it doesn't include some of the other things that are necessary. So net primary productivity is going to measure plant growth, but it's not the only way we can, or the only thing we can use to estimate. We have to consider other things. So what happens if humans grow beyond our carrying capacity? Well, we could see a population crash. We could just see this big just wipe out of humans. I mean, it's very possible, right? Disease could spread, and take out the entire population or the majority of it. That happened with the bubonic plague, and smallpox have been used to wipe out entire populations. Um, you could have these kind of boom and bust cycles because of stuff like that, or you could start to stabilize. And this is really like there's just barely enough food for one more birth, or somebody died, so now we can afford to have a baby. I mean, I'm oversimplifying it, but that's what that stabilizing is. Now there's something else. There's these ways of predicting population changes, and this thing called demographic momentum is that kind of lag between when you have a reduced birth rate and when the population growth actually begins to slow. So just because people aren't having babies doesn't mean that we're seeing the immediate effect of decline in the population. And that's visualized using these things called a population pyramid. So the higher up on the pyramid is the age of the individuals in the population, and the axis here, left and right, is the um, reproducing population. I'm sorry, not reproducing population, but the numbers of individuals in the population. And so the fatter means that there are larger, or there are more people in that particular age category. So this one has a very young population, whereas this one, the majority of the people, or the average age, is going to be a little bit older than this one. And the demographic momentum, which is the term that we're trying to illustrate here, is that this particular population is going to continue to grow for a while, because the younger aged individuals are still greater in number than the reproductive age individuals, whereas the reproductive age individuals over here in this population pyramid is about the same, or even maybe greater than the younger individuals. So that means that this population is going to not change very much, at least not in the next few generations. So other things that can affect growth rate, income, and women's literacy has been shown to reduce growth rates, because it delays motherhood, and women who are able to read are not having as many children. And so income, if you look at income versus growth rate, dollar amount versus growth rate, and also growth rate versus literacy, that data supports those statements. So public policies to decrease population growth, there's a lot of values and ethics questions here that I don't want to get into, because I am just a microbiologist. That's why I love my tiny world. Nobody cares if the bacteria scream. But some of the things that are suggested are access to education and healthcare, and the job market, and providing information and tools to regulate fertility and reproductive rate. Those are ways that the population growth can be adjusted using public policy. So hopefully after this very short video, how nice, you have a little bit more power to answer the questions about how the growth rate is affecting the human population and factors that have influenced the human population growth rate in the past, things like the industrial age and disease, access to vaccination. Thank you. Hillman, who developed 9 of the 14 childhood disease vaccines, single-handedly raising the average lifespan. Explain why populations go through a demographic transition. That's that drop of birth rate towards death rate. Define carrying capacity, so how much an ecosystem can support, and then list those density dependent, waste, access to food. I forgot the third one, so you're on the job for that one. Independent factors, things like natural disaster. Discuss those factors that may affect the Earth's carrying capacity for humans. So net primary productivity is one factor, but we have to think about things like access to fossil fuels and other resources. And then also the potential future of human population and what factors would help reduce growth rate. Well, access to education and a steady income have been shown to at least be correlated to reducing growth rate. Okay, well, that is the end of chapter 14. We did not skip, I'm sorry, we did not have a chapter 13, we skipped it. So I don't want you to panic. It went from 12 to 14. Okay, I'm going to end this meeting for all.